Dear participants, hello everybody from all over the world. I wish to welcome you all to a lecture in the section Combinatorics. My name is Alexander Schrijver from Amsterdam, and it is my pleasure to introduce our speaker, Julia Boettcher, who is Professor of Mathematics at the London School of Economics and Political Science in London, United Kingdom. Julia is an expert on discrete mathematics, in particular on graphs and hypergraphs, including large-scale networks, random graphs and networks, and packing and decomposition of graphs. With Matthias Schacht and Anus Taraz, Julia proved the bandwidth conjecture of Bolobas and Komloos. The topic of Julia's lecture today is graph and hypergraph packing. Julia, please go ahead. We are looking forward to your lecture.
Thank you very much for the introduction. It is a pleasure and of course a great honor to be giving this talk at the virtual ICM this year. So the topic of my talk today will be on graph and hypergraph packing. What I plan to do in the talk is to first start a little bit to tell you something about the origins and maybe some motivations of this area and give you the relevant definitions. And then I want to talk a bit about some results that have been proven recently, and I want to outline some exciting methods and machineries that have been used in order to achieve this. And then at the end of the talk, I want to summarize a bit where that leaves us now in this particular field, and wrap up with this. All right, good. So let's start and let's see where some of these problems come from. And I want to start with some historic examples. And I start with that of a Latin square. So these objects, as far as we know at least, first appeared in the 1700s. So what is a Latin square? A Latin square of size n by n is just simply an array where I have n rows and n columns, and I also have n symbols. And I want to put these symbols in these cells in such a way that in each row and each column, each symbol appears exactly once. And as I said, in the 1700s already, we know that some people looked at some example like this Korean mathematician here. And the name Latin square was then given to these objects by Leonhard Euler, who also got interested in them. It's not difficult to see that Latin squares exist, just because, and as in this example that I gave here, you can just simply put your symbols in some order and then cyclically shift this, as I have done here. So these exist for every n. But of course, you can ask for some additional properties that you want the Latin square to satisfy. So for example, if you talk about the 9 by 9 Latin square, where in each of the 3 times 3 subsquares of size 3 times 3, you have that all the symbols appear, then we have what we call Sudoku. And one can also ask for other additional conditions, such as the one that I will introduce on the next slide. By the way, this year is another famous Latin square, which appears on some window of one of the colleges in Cambridge. This is called Fisher Latin square. So Fisher was some statistician who noticed the importance of these objects for statistics. Okay, so I wanted to tell you about some other additional condition that you can put. And that brings us to an object called orthogonal Latin squares. So what are orthogonal Latin squares? That are just is a pair of Latin squares of the same size. And when I put these 2 Latin squares on top of each other, then I have so I use different symbols for the 2 Latin squares, different sets of symbols. And when I put them on top of each other, then I want that each pair of the symbols appears in some position. So where by pair, I mean a symbol from the first Latin square and a symbol from the second Latin square. So here's an example of size 4 times 4, where we just take the usual card deck, and I have the 4 suits, and I take Ace, King, Queen, and Jack, and then I want to arrange these cards in such a way that each suit appears once in each row and once in each column, and each of these card types appears once in each row and once in each column. Yeah, and this was a puzzle that was asked by this French mathematician here in the 1700s already. It's also a kind of nice puzzle if you want to occupy some children for a while to ask them to do this. Somebody else that was early interested in these kind of objects, orthogonal Latin squares, was Catherine the Great. She was not interested in 4 times 4, but rather in a 6 times 6 set of orthogonal Latin squares. And this was what became the famous 36 offices problem. So the thing was that she had somehow her offices was 6 in 6 regiments, and in each of the regiments there were 6 ranks, and then she wanted to parade them in such a way that in each of the rows, so exactly one person from each of the regiments and one type of rank. With one type of rank appears. And so what she asked in essence for was a 6 times 6 orthogonal Latin square. Now it was very unfortunate that she had these 6 regiments, because it turned out that, that for 6, you can actually not construct such an object, which was open for a long time and only shown at the beginning of the 20th century by some brute force search, that a 6 times 6 orthogonal Latin square does not, pair of orthogonal, so a pair of Latin squares that are orthogonal do not exist. And it turned out that so it was also known that for size 2, they don't exist. And it turned out that these are actually the only examples. Yeah, so Euler had already shown in the 1700s that these orthogonal Latin squares exist as long as we have 0, 1, or 3, mod 4 being n. And he actually assumed that for 6 times 6 these don't exist. But he also more generally assumed that in general for 2 mod 4, for n is equal to 2 mod 4, they don't exist. Turned out that was wrong, and they really always exist, but for n is equal to 2 or n is equal to 6. Okay, now these are 2 mathematical objects that I could be interested in finding, in counting them, and again, in finding certain types of them where I have some additional requirements that I asked for. What do they have to do with the topic of my talk, which was graph and hypergraph packing? Well, in order to tell you this, let me first get kind of to the basic definitions of this. So what do I actually mean by graph packing? So we have some graphs where, as usual, my graphs just have a finite number of vertices, and then I have edges between the vertices, and I don't allow multiple edges or loops. And I have a family of such graphs, and in this family I could repeat the same graph twice, that's okay. But here's an example, so that would be my family of graph. And then I have another graph, which I call H, and I want to pack these graphs into that graph, which just means I find copies of these graphs over here, and I find them in such a way that they are edge disjoint. So in that example, this would be a solution. I find this triangle here, and the second graph here, and then the third graph over here. And I don't use any edge twice with this. I could have some leftover edges. Here in this case, I have some edges that I didn't use. But sometimes we want to pack graphs which actually don't leave any leftover edges. And in that case, we call such a packing also a perfect packing. And this is also often called a decomposition of the graph H into the graphs that I'm packing. Sometimes I will also want to talk about near perfect packing, where the idea is that I use almost all of the edges and my leftover is somehow very small. Okay, so this is the definitions for graphs. Now I can analogously define the same thing for hypergraphs, of course, where in this talk, my hypergraphs will always be R uniform, meaning that every edge has the same number R of vertices, and the definition works in exactly the same way. Okay, so now that's my graph and hypergraph packing. Now, how do I translate these problems of Latin squares and orthogonal Latin squares into this language? Okay, let's go back to Latin squares. It turns out that finding a Latin square is nothing else than a graph packing problem in a setting like this. So what I do is I do a 3-partite graph, meaning I have n vertices over here, n vertices over there, n vertices over there, where the first set of vertices correspond to the rows of my Latin square, the second to the columns, and the third to the symbols. And I don't have any edges within one of these parts, but I insert all the edges between these parts. And then what I'm asking for is a partition of this graph here, which I call K and N, into triangles. Yeah, so a triangle would correspond to one of these entries in my Latin square, where I have the row, in this case number 3, and this is the column, and then I put the symbol A. Okay. Good, so this is a graph packing problem. Finding orthogonal Latin squares is also a graph packing problem, and all that I have to do is I have to put one more part. So now I'm 4-partite, so I have another part for my second set of symbols, and I want to decompose this complete 4-partite graph now into copies of K4, where the K4 again corresponds to one of these entries in this symbol with a certain row, a certain column, and now 2 sets of symbols. Okay, good. So so these are two kind of packing problems. What could we look at more general? Here is another thing that more general people were interested in, and that started a whole new area of discrete mathematics, so-called design theory. And these are also can also be seen as hypergraph packing problems. So what's a design? It's an object with 4 parameters. I have a ground set of size n, and I want to find on this ground set subsets, which are also called blocks of size q, with the following property. Whenever in this block I look now at the subsets of the block of size r, then any such R set is contained in exactly lambda of my blocks. Okay, so if I draw that as a graph, which schematically I try to do there, then the vertices are my ground set. I try to look for the blocks, which will be some complete hypergraphs, R uniform hypergraphs. And within these complete R uniform hypergraphs, the edges are the R sets. And I want that all the R sets on the complete hypergraph on all my vertices are covered exactly lambda times by such a block. And finding these kind of objects, that has actually a lot of applications. So we have applications, for example, in experiment design, in error correcting codes or cryptography. So these are important subjects. And as I said, their existence and what types of such objects we can create has been very intensively studied. So let me just kind of, to understand how these applications work, give you a little baby toy example of how these objects relate to experiment design. So, and for simplicity, when I do this, and also then afterwards, when I talk about the results, I will always choose lambda is equal to 1. In general, everything that I will say will hold for any constant lambda. When you allow lambda to grow with n, things become a little bit different, but let me exclude this from this talk. Okay. All right. So here's my toy application. So let's assume I want to do some experiment to test the efficacy of n drugs, because maybe some very nasty virus has appeared. And I want to find some drug or the best drug that I could use in order to fight this virus. And the challenge here is usually that it really depends on, I don't know, how old a person is, or on the sex, or on the ethnicity, how strong or in what way this drug will work. And therefore, it wouldn't be a good design of an experiment to just say we give lots of people all the different drugs and then we compare between 2 individuals, because individuals are so very different. Now, the solution that statisticians use in order to deal with this problem is what is called is a strategy that is called blocking. And what that means is they try to group individuals into blocks of similar characteristics, so that I get within a block people that I can compare with each other. And so now assume for simplicity that we just create such blocks or find people such that in each block I have q individuals. and that of all my persons overall, I give everybody one drug. Okay, and now what we want, of course, is kind of to compare all the drugs with each other. And therefore, in order to compare two drugs, I of course want to give them to two people from the same block. But in order to do this in a particularly efficient way, I also want that each pair of drugs only appears within one block and not in multiple blocks. And that's exactly asking for a design, or in other words, for a decomposition of the complete graph on n vertices into complete graphs of q vertices. And of course, here there are a lot of simplifying assumptions. So experiment designs in the real world will of course be very different, but this is maybe kind of the most simple scenario that one could imagine. Okay, so designs have important application, and one of the most fundamental question, of course, is that you can ask is when do these designs exist? Now let's go back to our case that we are just in the graph world, and so a design, we said, corresponds to decomposing a complete graph into cliques. And in this case, I just want to look at the simplest example, namely that I decompose into triangles. Now, it's of course very easy to see what are some conditions that I need in order for such an object to exist. And for example, of course, I need my number of edges to be divisible by 3 so that I can cover all of the edges by edge disjoint triangles. But I also need that the number of edges on each particular vertex is divisible by 2, because whenever I put a triangle here, it eats up 2 of the edges. Okay, so these are some very easy conditions, and you cannot just formulate them in this very easy case, but you can formulate them in general when you are in an R-uniform hypergraph and want to cover that with complete hypergraphs of size q, then you get some analogous conditions to these I formulated here. And the very important conjecture was that whenever these natural divisibility conditions, they're called, are satisfied, then we can actually find such a design for the parameters n, q, and r. Which is not quite true, because there are some people, it was very early on noticed that there are some small counterexamples, but as long as we exclude these small counterexamples, then these designs should exist. And this turned out to be a very difficult problem. So for this easy example here of graphs and triangles, this was already done very early on by Cookman in the 1840s, but then it took until the 1960s until anything more could be done. So in the 1960s, this was done when the triangle is replaced by a K4 or a K5, and the very basic case for 3 regular hypergraphs, where we want to tile it with complete 3 regular hypergraphs of size 4, was also done then. And then it was a big breakthrough when in the 1970s, Wilson actually solved this problem for all graphs. But it seemed that higher uniformities, that this really needed some new ideas and some new tools also. So this was one of the big recent breakthroughs in the area by Kivash to show that for all R and Q, designs exist whenever n is large. And what I want to do next is I want to talk a little bit about the proof method behind this theorem, and want to highlight what are the important ingredients here. All right. Good. So in this outline of the proof method for illustration, to make it easy, I will just look at the graph case and again the case that we want to pack triangles as before. So here is the first ingredient that is important for this proof, and that is randomness. And that's actually an idea that is around for longer already. But before I talk about this, let me first say what is actually the idea. The idea is somehow I want to pack triangles randomly in this graph. And my first idea here could maybe really be just to throw in triangles randomly, one by one, and continue doing this. Now, there very soon we noticed that this is not a good idea, because as soon as I pack lots of triangles, then I will have many, many overlaps if I just throw them in randomly without being careful of whether they use an edge that has been used already before. So that's not good. So we need some refinement, and the refinement actually came already in the 1980s by a method that is now famous and is by now called Rödel-Nibble. So this was invented by Rödel. So what was his idea? The idea was, well, we still should select triangles randomly, but we do this in rounds. And so in the first round, we throw in a small proportion of all the possible triangles randomly. Of course, there will be overlaps, but whenever I see an overlap, then I just remove the triangles that are involved in an overlap. Yeah, and if we only put in a small proportion of the possible triangles, then one can easily show that there will only be relatively few overlaps. Okay, what do we do then? Well, then we have selected a number of triangles that we want to use in our packing, and now I just delete the edges that I used in there, and then I do a second round of randomly throwing in triangles and so on. And why is this possible? Well, this is possible because what one can show is that after each of these rounds, what remains of the graph has certain quasi-randomness properties. So the edges are very nicely distributed. And that makes what makes this work. And it's called the Rödel-Nibble, because the idea is really we kind of start nibbling the cake, and we in each round nibble away a very little bit. And by doing this, we eat up almost all the cake. And then, of course, at the end, because we are polite, we leave over a little bit. Or to kind of come back to mathematics, of course, at the end, we won't have covered all the edges of the graph, because at some point this method will break down and I cannot use pure randomness anymore in order to cover the remaining edges of the graph. Okay, so we need a second ingredient, and the second ingredient should really deal with this problem. I have some random process here that covers most of the edges of my graph, and then at the end I will have some leftover. So now what about this leftover? So what we use in order to deal with this leftover is also a famous method within combinatorics, and that's what is called the absorbing method, which has been used in many flavors and is around in extreme combinatorics for quite a while. But in this setting of packing graphs, it has really only been successfully used within the last, say, 10 years. Okay, so what is the basic philosophy of the absorbing method? The basic philosophy should be, so our random process will leave some leftover. And we know this before we start our random process. So maybe before we start the random process, we should prepare for this and somehow find some very clever structure which will help us in the end to deal with this leftover. Okay, so now this is a bit philosophical. So let me try to make this a little bit more precise, again with some baby example that doesn't really represent what happens in reality, but should give you some feeling of what this absorbing does. Okay, so let's think a bit about this leftover here. What could this leftover be? Now, if the leftover itself is just a collection of edge disjoint triangles, then of course we are happy, right? And because then we can just take these edge disjoint triangles, add them to the triangles that we created with our random process, and we have a decomposition, and we are happy. All right, what else could it be? Well, for example, we could have a scenario like this. So let's assume for simplicity that our leftover is a cycle on 6 vertices. Now, at first, this looks really bad because there are no triangles left in this, so I cannot add any triangles to my edge decomposition. But what we can do in this case is the following. Now, let's assume that we were somehow clever at the start and somehow managed to guarantee that we also have in our collection of triangles that we already have these set of triangles. So these triangles that I shaded in red here, of which there are 6. So let's assume we have these, we have guaranteed that we have these triangles in our collection of triangles. Then I can do the following thing. Then I can say, okay, I have these triangles, but now I can switch. What I want to do is I want to switch from the red triangles to these white triangles over here and use these instead. So these are 8 triangles. And what is their property? Well, these white triangles use exactly all the red edges that came in my red triangles, but also the blue edges that come from the C6. And therefore, this structure here of red triangles has absorbed this leftover in the form of the C6. Okay, now, of course, in reality, our life is much harder because our leftover is a lot bigger. It's not just a constant number of edges. It's a lot bigger. We don't really have any control over what it looks like. It could be anything. So we will need to do some much more clever structures in order to absorb the leftover. Also, we cannot hope usually to do this in one step, but we have to do several rounds of this. And what Kivasch's proof does, it introduces some very clever techniques which are based on some algebraic structures and some more randomness in order to do the absorption. By now we have a second proof also of this result, which again uses this basic philosophy of a proof, but works very differently in the absorbing step. So the second proof is by Glock, Kühnlo, and Osthus, and they use a method which is called iterative absorption. So lots of interesting and powerful methods have been invented here, and this turned out to be really useful for the field because it has influenced some other problems and led to the solution of some famous problem very recently. So here I really just list some examples that are very recent, such as Boettcher and Kivasch's work on the n-queens problem, where I want to place on an n times n chessboard either a normal one or a toroidal one, n queens, so that they are non-attacking. And the question is, how many of such configurations exist? And they solved this question. There are also other questions in Latin squares. So for example, the very well-known conjecture said that in any Latin squares, there's always a transversal of size n-1, where n is the size of the Latin square. And the transversal just is a collection of cells that I have such that I have exactly one cell in each row, one in each column, and each symbol only appearing once. And this has very recently been solved by Montgomery. There's also related questions concerning transversals in subsquares of multiplication tables of abelian groups. And again, these methods here played a very important role in the solution of this. And another famous example is some recent solution to a coloring conjecture on hypergraphs. Okay, but that is mainly to stress that these methods are powerful and important and have lots of influence also on other problems. Okay, so let me now, after this chapter, talk a little bit about, okay, we have designs now, we know how to find them, but what kind of other packing problems could we be interested in? And here again, I want to go back to some historical example, and that is the example of the so-called Cookmans Google problem. And what is that? So that problem appeared in the 1850s in this obscure journal published in London, and it said the following, and here you should think, I don't know, respectable English girls' school. So we have a class of 15 girls, and they should go on a walk each day for the 7 days of the week. And we always want to put 3 of the girls next to each other. And we want to do that in such a way that no 2 girls walk next to each other or will walk in one of these 3 groups on 2 of the different days of the week, maybe so that they don't get too acquainted with each other and then chat the whole time. All right, good. So what this asks for, in other words, if I translate this to the graph packing problem, graph packing language, then I ask for a packing in the complete graph on 15 vertices, because we have 15 girls, And I want to pack triangles there, but I don't just want to pack triangles, but I want to pack collections of triangles, namely 7 collections of such triangles, one for each of the days. And these collections of triangles should be vertex disjoint and cover all the vertices. In other words, we ask for a decomposition of the complete graph on 15 vertices in what we call a triangle factor. Now here's a triangle factor. So I just have triangles which are vertex disjoint and cover all the vertices. And so one of these triangle factors should represent one of my 7 days. So I can do it for the first day, and then for the second day, I should pack another triangle factor, and I shouldn't use any of these edges again. So here is a possibility to do this, and then I have to do it again for the third day, and then for all the other days. And here is a solution how to do this in this particular example. And the question, of course, is again, when can I have when can I pack these triangle factors? And again, I have some very natural divisibility conditions. So in this case, of course, 3 needs to divide n because I want to cover all the vertices with my triangles. And I also, again, need that 2 divides n minus 2 because every triangle, again, eats up 2 of the edges at a vertex. In this problem, of course, I cannot only ask for packing triangle factors into a complete graph on n vertices. I can also ask the same thing for kq factors with larger q, and I can again go to R uniform hypergraphs. And these kind of objects are called resolvable designs. All right, good. So how do I find such resolvable designs? Well, it turns out that I can actually translate this problem of finding resolvable designs into a design problem in a apartheid setting. So let me just show you that at some example. So let's assume we want to find triangle factors, as in the previous example, in a complete graph of n vertices. Now, what I can do is I can add another little set of vertices here, where I add one vertex for each of the triangle factors that I want to add. So in our example of the 15 schoolgirls, it was 7 triangle factors that I was looking for. Then I would add 7 vertices here. I don't put any edges on these additional vertices, and I put all the edges from these vertices over to the complete graph. And that's why this is a apartheid setting. So I have one part here, which is independent, one part here, which is complete, and then I have some edges in between. And now let me assume that I can find a decomposition of this object here into copies of the clique on 4 vertices, so K4s, just such as this object here. All right, so what happens? Well, if I have such a decomposition into K4s, it's very easy to see that each of the K4s has to use exactly one of these vertices and then 3 vertices over here, because otherwise the number of edges would not add up. And if that is the case, then of course, if I now look at all the K4s that are adjacent to this vertex over here, and I didn't draw all the edges, then it turns out that these, if I only concentrate on the complete graph over here, will form a triangle factor. Yeah, so that's one of my K4 copies. This one here would also be all connected to that vertex. That would be another K4. Now, of course, this triangle here cannot overlap with this triangle. Otherwise, we would use one of these edges again. So having a decomposition into K4s of this object gives me a decomposition of this complete graph into triangle factors. And fortunately for us, Kivash generalized his result to also deal with scenarios where I work with such apartheid settings. And in fact, he also generalized it so that more generally, I am allowed to color some edges and then also color the edges of the things that I'm packing in a certain way. And I'm also allowed to have directed edges. And then as long as some suitable conditions are satisfied, I can do the packing. And that again turned out very helpful for the area that allowed to address a number of other problems in the field. And that's what I want to spend the next few minutes on talking on one type of these problems where this was helpful. And that is some work that I was involved in. And that kind of brings us a bit further again to the question, what kind of other objects we could pack. So here is one other example of some packing conjecture that has been around for some time and which concerns some other objects. In this case, what I want to pack is a family of trees. So this is the conjecture by Giafas from the 1760s. And in this conjecture, I have a family of trees, and my tree number I has exactly I vertices. But other than that, I don't have any restriction. And the conjecture says no matter how you choose these trees, you can pack them in the complete graph on n vertices. So here's an example where these trees are packed. Where does this conjecture come from? How does it come about? Well, I mean, one thing is that really some number magic is at play here. So what happens? So if I look at the number of edges in total that I want to pack, so I sum up the number of edges in these trees, tree number I has I vertices, so it will have I minus 1 edges. And if I do this sum here, then I get exactly n choose 2, so the number of edges that I have available in my graph. So if I can do this packing, then this will be a perfect packing, and that's somehow what makes the conjecture challenging. Now, for a long time, apart from this number matching, not much else could be done about this conjecture, and it was only possible to prove it in some really special cases. And then these ideas of, first of all, randomness, and then later also absorbing that I tried to introduce to you, they really made a big difference on this conjecture. And after some work by some colleagues, important progress that they made, we managed to prove this conjecture in joint work with Ellen, Clemens, Slatky, Piggy, and Taras in a sequence of papers for trees with maximum degree Cn log n, where C is some small constant. So for trees which have kind of almost the maximum degree that you could get, but not quite. And I can say just a very tiny little bit where this bound comes from. And we also require that n is large. Okay, how do we prove this conjecture? So the starting point for the proof idea is the following. When we have a tree, then we know, because if it has n vertices, it has n minus 1 edges, so the average degree is below 2, and so it's very easy to show that either they have to have linearly many leaves, where a leaf is just a vertex of degree 1, or linearly many bare paths, where a bare path is just a sequence of vertices that form a path, and where the inner vertices don't have any other edges coming out of them. And all these paths should have a certain length. So, for example, you could choose that you want to have bare paths of length 10, and then you can find linearly many of them. Okay, so because we somehow have this dichotomy, the basic proof strategy could be that, okay, we have a family of trees here, and they of course look different, but kind of many of them have to have many leaves, or many of them have to have many bare paths. So I select whatever is prevalent more often, and then remove either the leaves or the many bare paths. I then find an almost packing of whatever remains after this removing, and then I somehow want to complete by embedding all the leaves and bare paths. Now, for the first step for finding this almost perfect packing, I again want to use some random process, which is different from the random process that I showed you before, but it's a very natural random process, not difficult to formalize. And the difficulty comes in here really by asking. The difficulty here really is to analyze this random process. Okay, so for the second step, about how to complete the embedding, it turns out that kind of there are two different things. Either I have leaves, and it turns out when I have leaves, then I can just use, again, some randomness, surprisingly, some random matching strategy in order to put back the leaves. And in the case that I have many paths, my strategy instead is that I want to reduce my problem to a apartheid colored direct decomposition problem, and then use the result of Kiepers. Now, that is the basic philosophy of how we prove this result. None of these steps is easy. So this analysis of the random algorithm here, that takes about 40 pages. Then putting these leaves by some randomness, that takes another 50 pages, and then doing this reduction step that takes about 150 pages. So it's not easy. One has to do quite some analysis, but putting that all together, then we arrive at this result here. All right, so where does that leave us in the field? So I showed you some results on designs, and I showed you some packing results on trees. I showed you what kind of other problems this relates to. I've actually left out, for being concise here, I left out a lot of other results that were proven. So we have other packing results for cycles, solving, for example, the famous Oberwolfach problem, and so on. So there are other results and lots of other colleagues that worked on problems like this. And for brevity, I left out a lot of citations and would like to apologize for this. But there's really a lot of things that we still don't know. So for example, if we stay with graphs, now, of course, already, if you look at this tree packing problem, we don't have the full conjecture yet. We have this bound on the maximum degree, which comes from these random processes here, that's what they can deal with. And the question is, how do you remove this? There's some hope of doing this because important work on a related tree packing conjecture was done where one doesn't need this. So that's some exciting progress, which was done by Montgomery, Prokofsky, Zudakov, and independently by Kivash and Staden. But we can, of course, also ask, what about other structures that we want to pack? What if instead of trees, I want to pack some more general planar graphs? Under what conditions can I do that, and what are the parameters that limit me or that guide me when this is possible and when it is not possible? And that we don't really know yet. And once we go to hypergraphs for these larger structures that we want to pack, then even less is known. So there's lots of open work here, so lots of open problems where work has to be done in this field. And that brings me to the end of my talk, and I would like to thank you for listening.
Thank you very much, Julia, for your very beautiful and inspiring lecture. The audience cannot ask questions, unfortunately, but I can say for this result of Peter Kivash, or also for your result on tree packing, how large is N, say for Kivash, N compared with Q and R? Is it computable at all? Or is there a formula?
Yes, one can compute it, but yeah, I mean, we certainly didn't try, neither did he try. So these bounds on N, they really come from the analysis on the randomness that is involved. So you want certain concentration inequalities and so on to hold, and then you kind of just need to see how big has N to be. So it's not extremely horrible, I would guess, but yeah, it's very large. So that's another question. What if N is smaller? And that's, of course, the question that in practice people are interested in. So yes, work in design theory is not over.
No, is it computable at all, or some bound computable?
I would think it's
like in your case on tree packing.
Yes, it is completely computable, but we didn't try.
Okay. Thank you once again, Julia, for your nice lecture.
Thank you very much. Thank you.
Thank you. And thank you also to the audience for their attention. And thank you for Kim for organizing the session. Thank you.